Okay, so we'll probably start in just a few seconds here, but for people who are on the Zoom, just note that John said, please feel free to unmute and interrupt if you have questions during the talk. Yeah. So are you ready?
Yeah.
Okay, great. So we're delighted to have John Bourke here talking to us about tensor products, multimaps, and internal HOMs. So floor is yours.
All right. Thanks very much for the invitation. It's a pleasure to give a talk to you at the Topos Institute, and it's going to be a kind of expository talk, so there's not that much new research, though we will cover some things I've done. Whoops, so I'm still getting used to this. Let's see, there we go. So what's it about? So, well, it's kind of about Skew structures, but it's a story of how I became interested in them, which I'm not sure that everybody knows that well. And I think it sort of motivates them pretty well. And it builds on thinking about three closely related concepts. So these are multi-categories, everybody knows and likes. So there where you have these multi-maps like this, and then monoidal categories, which are probably the best known of these sort of three concepts, and that's where the crucial feature is a tensor product. And then so there's the less well-known of the three, which is closed categories. So here, the key player is the internal HOM. So these are very closely related, and the relationship between them is well understood. But exploring the relationship between them, which is what I'm going to do in a careful way, naturally leads to skew variance, and that's what I'm going to tell you about. And also, more specifically, how I came to come to them in my own research, in a sense, and apart from just liking this story and some examples and some of their curious features, which I think people also don't sort of appreciate that well. So, all right, so I'll start with the best known of these, and I think most people know about these monoidal categories. So I guess they were introduced independently, I think, by MacLean and Benabou in '63. It's a very simple idea to us now. So the idea is you want to categorify the notion of a monoid. So what does that mean? It means you have, instead of a set, you have a category, and you have a tensor product functor, and you have a unit object, and then you have, instead of the associativity and unit equations, which there's three of those, you replace those by natural isomorphisms, okay? Like that. And so in the notion of monoidal category, MacLean's original definition, I believe Benabou's was infinitary actually, so they're not exactly the same by definition. There were 5 axioms that I like to label like this. So they refer to the objects in the axiom and the order in which they appear. So A, B, C, D means 4 objects, and that's MacLean's pentagon. So there's also 3 axioms involving 2 arbitrary objects in a unit, and you can stick the unit wherever you like. And then you get 3 axioms, and then there's another axiom with just 2 copies of the unit. So that was the original definition. And so Max Kelly, the next year, he showed that 3 of those axioms were redundant. Though redundant axioms sometimes, can be confusing in future years. So these axioms generate all in a certain sense, and that's MacLean's coherence theorem. And So the classic examples, motivating examples, would be things like Cartesian product of sets and the tensor product of vector spaces. Okay, these satisfy these sort of things. Okay. So next I will look at closed categories. So I don't know exactly, I feel like some of this stuff may have kind of been around for a little while, but in some form or other, these were ideas were going around at this time. But the first really big treatise on all this sort of enriched category theory and stuff like that was the monograph of Eilenberg and Kelly in '65. And so there you've got the core player is the notion of a closed category. And here, instead of the tensor product, you focus on the internal Hom, okay? And a unit object. So these are abstract notions, internal Hom, unit, and I'm just giving them names. And so that's all pretty nice. But instead of the associator for a monoidal category, we have this guy L, okay? And then we have a map you can think of as evaluation, which is supposed to be invertible. And then we have the map J, which you think of as picking out the identity, okay? And these satisfy 5 axioms again. And I should mention these maps. There's contravariance in the definition, or there's contravariance in the internal Hom, which leads you to consider naturality in contravariant variables as well. So you need to consider extra natural transformations. And so far, we only had one thing invertible, that's this I. But we also, in the definition of a closed category, we asked for this map down here to be invertible as well. So you can think of this map as viewing a morphism of your category as an element of the internal Hom, if you think of it that way. And well, this essentially says that morphisms of the category are the same thing as elements of the internal Hom. Okay, so that's a closed category. And so let me point out some curious stuff. So as before, we've got 3 transformations, 5 axioms, but whereas before we had 3 invertible things in monoidal categories, now we only have 2, okay? And we can look at our vector spaces example again. Here, Hom A B is the set of linear maps from A to B with the pointwise structure, okay? That's just one example, but yeah, maybe I can say a few more words about closed categories. So as I mentioned, the first major treatment of enriched category theory, first book on it, used closed categories instead of monoidal ones as the core. That was Eilenberg and Kelly's closed categories monograph. Why was that the case? Well, I don't know the answer, but I expect the reason is that it's often easy to say what an internal Hom is, say what its elements are, like in the vector space example. Whereas, and these internal Homs are often described as limits corresponding to that fact, but tensor products usually involve some sort of co-limit, and their elements are less explicit, like in the tensor product of vector spaces. So perhaps that's the reason why they chose to use closed categories as the core rather than monoidal ones. I don't know, but that's what I guess. And so that's great. So that's one advantage of closed categories. But then the annoying thing about them is that they're axiomatics. You end up doing all this stuff with iterated contravariance. Once you put L's together in the first variable of something and then it becomes covariant again, it becomes a bit hard to keep track of, hard to parse, to know whether you've written something correct. It's one of the disadvantages of closed categories. Okay? now. So the third player in our story is the notion of a multi-category that was introduced by Lambeck in 1969. And so here we have objects, and we have multi-maps between them, as I've depicted. And so what else do we have? So we have some unary identities, identity morphisms, and then you can compose these multi-maps in the way I've depicted there. That's called substitution. And this substitution identities that satisfy associativity and unit laws, as we expect. One difference here is that in the case of a multi-category, you have infinitely many substitutions and infinitely many axioms, though a finite scheme of them, a finite scheme of axioms. So that's a difference between all of these other definitions. Okay. I should mention Gabriele Lobbia and I have been looking at this relationship between the three things and also looked at finite definitions of multi-category. And he talked about that at CT, but I won't say any more about that. But so that's the definition of a multi-category. And a good example would be vector spaces and multilinear maps. Okay. And so another example that motivated Lambeck were sequence like this in the sequent calculus. This was one of his other guiding examples, and he studied the relationship between multi-categories and proof theory and linguistics and things like that. I'm still not really on top of it. We've got a reading group for students this semester where I'm hoping they're going to teach me that stuff properly. So, but one thing to mention is that in a multi-category, you just have a set of objects, but because you can compose unary maps, you get a category of unary maps. So you can also think of this as a category with structure, like in our previous examples, okay, of monoidal category and closed category. And yeah, so moving on. So an important theorem of Eilenberg and Kelly in their monograph that I call the Eilenberg-Kelly theorem is the following one. So it relates monoidal and closed structure. So it says that in the context of a category with a unit object, a tensor product bifunctor, and an internal Hom, with these related, so I'm using juxtaposition for the tensor product sometimes, and suppose the tensor product and internal Hom are related by adjointness, so natural isomorphisms like this. So as in category theory, at least people are familiar with, then the nice thing is that there's a bijection between extensions of the category equipped with the tensor product and the unit object to a monoidal structure. So putting in the associator, the left unimap, the right unimap, this stuff. There's a bijection between that and extensions, on the other hand, of the category equipped with the internal Hom and the unit to a closed category. But not quite, because you have to add in one more condition, which is that a certain map, which I'm not going to explicitly describe, is invertible. Okay, so you can think of that map as being a sort of internal version of the adjointness that we saw in the isomorphisms above, but it can be described using the closed structure together with the adjunctions. But the annoying thing about it is that it involves both the monoidal closed structure and the closed structure, right? So it's not something that's purely definable using the closed structure. So we have a bijection between monoidal structures and closed structures plus some other annoying condition. And what's the idea? So I'm not going to prove it properly, but the point of the proof is it's a very natural thing. So each of the transformations on either side matches up one to one another in a sort of bijective way. So the associator corresponds to this slightly scary map L, which is the complicated one in the closed category. And then the two different kinds of unit maps on either side also match up. And the axioms all match up. And moreover, the only problem is that on the monoidal side, we have 3 invertible maps, right? But on the closed side, we only have 2 invertible maps. So to fix the correspondence, we have to add in another condition, which is the extra condition about the T, requiring it invertible. That corresponds to the associator. So T is invertible if and only if the associator for the monoidal structure is invertible. Okay, does that make sense? So, but there's an imbalance here, which is that nothing on the side of a closed category corresponds to the invertibility of the associator. Does that make sense? So there's an imbalance between closed categories and monoidal ones, because across this correspondence on the monoidal side, you've got 3 invertible things, and on the closed side, only 2. So you can have closed categories that give rise to things which aren't quite monoidal, but which in fact have a non-invertible associator. Okay? So this naturally leads to the question of how do we fix this imbalance in a natural way? And that's the story of skew structures. Okay, so this is a bit of a joke. Let's invert some isomorphisms. You can't invert isomorphisms in a category, but you can get rid of the isomorphisms in the definition of a monoidal category or closed category. There's no canonical way to do that in the case of a monoidal category, right? So you have to choose orientations and stuff like this, and it's not entirely obvious how to do it, but it's easier on the closed side because the things have a more obvious orientation. This isn't the historical way the concept came up in the literature, this story I'll now tell you, but it's the way I came to it myself, and it's essentially following the line of thought of Ross Street, and indeed his paper, Skew Closed Categories. So the point is, we want to get rid of invertible stuff in the definition of closed category. Well, that's pretty easy. So we just have an internal hom as before. We have our unit as before. We have our 3 extra natural families. The only difference is that we only require this middle map. We don't require it to be invertible anymore. That has quite a natural interpretation or a natural orientation, because you generally think of that map as a valuation, say at the canonical element of the unit. Okay, so and so we have this other map J, and we have the same 5 axioms as before. Please do interrupt me if anyone does get lost. But okay, so does that make sense? So the notion of a skew closed category, all you had to do actually was make this one non-invertible, and then the other extra condition there was an extra condition in the notion of a closed category down here, saying where you had another map's invertible, we don't ask for that either. Okay, so that's the notion of a skew closed category, and that was introduced by Ross Street in 2013. The notion of a skew monoidal category was introduced the year prior to that. That's by Cornel Slachani. And so in a skew monoidal category, you have the same basic stuff. You have a tensor product and a unit, and now you have natural transformations oriented like this. So the orientation in the monoidal case is absolutely not clear, because previously all of these were invertible, and it all seems a bit random really when you see it. And you have the same 5 axioms as before. So when I saw this definition, I didn't like it at all. I was thinking, what is this obscure structure? Who cares about these? Because it seems very non-canonical in a way. And in category theory, we like to think of, we're sort of happy with the notion of a monoidal category. It's a coherent categorification of a monoid. What on earth is this? How can we conceptualize it? But so note the orientation, I guess, is one of 8 possible choices that you could have, since you could orient each of these 3 maps in a certain way. Unlike in the case of a monoidal category, none of those 5 axioms are redundant, okay? So Kelly showed that 3 of the 5 were redundant for monoidal categories, but in the Skew case, none of them are redundant. So I guess that was a bit of a challenge coming up with this definition as well, because mostly when people think of the definition of monoidal category, they just think of the 2 axioms. So these 3 axioms have to be recovered. Okay, so what I consider Street's theorem then is the rectification of the Eilenberg-Kelly theorem. So what is this? So it's got the same basic structure. So you've got a category, a unit object, a tensor product functor, some internal hom, and you've got natural isomorphisms like this, okay? And now we've got the Street's theorem gives the perfect correspondence. So, whoops, what am I doing? It says that we've got an extension of the category C plus the tensor product plus the unit to a skew monoidal structure, and a tensor and an extension of the category with the internal hom and the unit to a skew closed structure. And there's a bijection between them. So this gives you a perfect correspondence in this way, okay? And I found this very, very pretty when I saw it, having been a bit unsatisfied about the original theorem. Of course, it's the correct theorem, and there's nothing unsatisfactory about it. It just, the fact that there was an imbalance between monoidal and closed structures. Why, if they essentially capture the same thing, why does one of them only involve 2 invertible things and the other one 3? And I tend to think of the Eilenberg-Kelly theorem as a refinement of the above. It says things like, in the context of the above theorem, there's the associator for the skew monoidal structure will be invertible if and only if the map T that we saw before was invertible, or one of the unit maps on either side will be invertible if and only if the unit map on the other side will be. And of course, and you can actually generalize this in different ways. So in the 2 categoricals, I actually give a model categorical generalization or a homotopical generalization of this in a later paper. But so you can, if you have one of these situations where you have tensor products and units, or tensor products and internal homs related by adjointness like this, you get all this extra structure, associators, the map L, all related like this, and you can call them monoidal skew closed or closed skew monoidal structures. Okay. Anyway, that's how I came. So through the work of Street, I felt that this was a very natural concept, but I haven't told you about any examples at all yet. So let me move now to examples of skew monoidal categories. So one I will just go through very quickly because they're not the ones that motivated me. But Slachani's original examples that motivated him come from bialgebras and bialgebroids. Okay, so suppose you have a bialgebra in a symmetric monoidal category, I've said here, but you could just think the category of vector spaces or something like that. Well, then you can describe a skew monoidal structure where the tensor product is the tensor product of your symmetric monoidal category, but with the bialgebra stuck in the middle. And your unit as before. So I've written the associator and units for the skew structure using string diagrams. Okay, so if you look at firstly at the units, these are kind of obvious. The units for the skew structure, you just use the co-unit and unit for the bialgebra. And on the other hand, the associator is kind of complicated. It uses both the multiplication and co-multiplication. And so this gives you a skew monoidal structure on the same category, okay? And indeed, the associator will be invertible if and only if the bialgebra was a Hopf algebra, for example. So I haven't really explained why these are interesting at all, but Slachani was interested in them because you can classify or even define bialgebras and bialgebroids using such skew monoidal structures, and the definition of a bialgebroid, the direct definition, is quite complicated, but this gives a conceptual approach to it. There's other very interesting reasons, and I will, in a sense, come to them when I move to the section properties of skew monoidal categories, okay? But for now, I just want to talk about examples. All right, so that's one example. That's the original one. Here's another one that I like. So if you want to, so there's all these new sorts of theories floating around. So we all know monads and things like that, but there's a few new ones like relative monads arising in theoretical computer science, or operatic categories, which generalize operads but describe structures beyond the scope of operads. And usually you can define, for example, a monad as a monoid in a monoidal category of endofunctors, as people like to say. Sometimes it's not considered the most illuminating definition. But what about if we want to understand, say, relative monads, which is a new notion, as monoids? Here we have to go skew. And so what's the idea? So take any functor, okay? And suppose your category, your codomain category, admits left can extensions along that functor. So for example, if the category A is small and the category E is co-complete, which are very general conditions. So in the paper, monads need not be endofunctors, Altenkirch and Ustalu showed that the functor category, the category of functors from A to E, has a skew monoidal structure. So since we're looking at functors from A to E, there's no obvious way to compose them. But so the unit will be the functor I itself, okay? And so the tensor product of a pair of functors F and G, well, what do? You take the functor F and you left can extend it along I, which we know we're allowed to do, and then you can compose that with G, And that gives you a new functor, which is going to be the tensor product in this skew monoidal category. Okay? So if you've ever seen things like composition of profunctors or distributors, or whatever they're called, that's very analogous to this, where you would take E to be, to be the pre-sheaf category, and you're extending along the innate embedding. That's this sort of, that's how profunctor composition works this way. So I won't tell you what the unit and the associator are, but they just come from the universal, come from the CAN extension structures and the universal property of it. And Chapman, thank you, that's right. Thank you for that. I should have checked my references before giving the talk, actually. I was creating a reference page at the end, but I sort of ran out of time, so I hope I haven't missed any more names anywhere. So this functor category is skew monoidal, and now a monad or a monoid in this functor category is what's called a relative monad. And so in classical settings, often this structure tends to be monoidal. So if I is fully faithful and dense, that automatically forces the unit maps to be invertible. And there's another not so simple condition that forces the associator to be invertible. But in classical situations, these are satisfied in many classical situations, like the inclusion of finite sets into sets, which is relevant for things like Levier theories and finite tree monads and set. But they're not satisfied in other more exotic situations related to things that Richard Garner and I looked at in our paper, Monads and Theories, where we had these nervous monads, so that are relevant to higher dimensional category theory. And okay, so another example of this phenomenon was described by Steve Lack. So he described these operatic categories as monoids in a skew monoidal category. Okay. Now, these are some examples. Let me tell you about how I came to the subject, which is from two category theories. So the way I was thinking about these structures was that in a skew closed category, we have this canonical map which views morphisms from A to B, that's things over here, as you can think elements of the internal home, that is maps from the unit to the internal home. And the thing is that in a closed category, one of the axioms was that this is invertible, okay? That was one of our two invertibility conditions. But in the skew setting, this doesn't need to be invertible. That's not an axiom. And the way that I interpreted that is that in the skew world, what this actually says is, well, we have a way of viewing morphisms from A to B as elements of the internal home, but not necessarily every element of the internal home arises in this way. So the internal home in the skew setting contains the morphisms from A to B, but it might contain some other stuff as well. Okay, so you can think, so my perspective of skew structures is that they're like classical ones, but they allow somehow for fattened up internal homes where you put some more stuff in. And for these, so these could be, for example, weak maps, okay? This is how I got interested in it. And you see in two category theory, this idea fixes various sort of problems actually. So first of all, in two-category theory, we have strict maps and weak maps, pseudo maps, lax maps, op-lax maps, all this sort of stuff. For example, there's a two-category of symmetric monoidal categories and strict symmetric monoidal functors and symmetric monoidal transformations, okay? And on the other hand, perhaps more interesting is the two-category with the same objects, but more maps. So strong symmetric monoidal functors, or even lax ones, if you prefer, and symmetric monoidal natural transformations. Now, the left-hand side is better behaved. It's in the sense of enriched category theory. It's complete and co-complete and all this sort of stuff. But the right-hand side is perhaps of more interest. And one of the techniques of two-category theory, in particular, the Australian school, is to study these sort of things on the right, using these better behaved things on the left. That was all this two-dimensional monad theory of Blackwell, Kelly, and Power. And okay, so what I'm talking about now is a phenomenon of that nature. So as a two-category, the two-category of symmetric monoidal categories and strong symmetric monoidal functors has a closed monoidal bicategory structure. So this is a kind of slightly terrifying definition, the notion of a monoidal bicategory with lots of axioms. But you can think of this as a categorification of the monoidal category of commutative monoids or vector spaces or something like that. And one thing about it is that the internal hom is quite simple. So the elements are the objects of this strong symmetric monoidal functors, and the morphisms are the symmetric monoidal natural transformations. Whoops, I keep doing that. And so here, the structure is symmetric monoidal category is pointwise. That is, you just define the tensor product of symmetric monoidal functors in a pointwise way. So f tensor g of x is equal to f of x tensor g of x. But it's all a bit complex because the monoidal bicategory structure is weak. But the thing is that these homs, where you have the pseudomaps in them, actually restrict to the two-category of strict maps and give a skew monoidal closed structure there. So something that's definable using ordinary enriched category theory, if you like. Okay? And so the point is that this two-category here has strict maps as morphisms, but the hom, which is the natural hom, has weak maps as objects. And because we have this mismatch between the morphisms of the category and the elements of the hom, which are more general, that tells us we have to be in the skew world. Okay? So what happens here is that in this, if we take seriously this concept of studying the non-strict world using the strict world, well, what happens when we study these monoidal bicategories is in passing to the strict world and using that to study it, where we end up with the concept of a skew monoidal structure. So we can think of skew monoidal structures in the two-categorical world as sort of strictifications of monoidal bicategories. But so I could go on, and these skew monoidal structures are very cool. For example, the associator and unimaps are weak equivalences. If you have all the objects fibrant and cofibrant, and I call these things homotopy monoidal because it ascends to actual monoidal structures in the homotopy category. And I worked all this out for model categories generally. So there's a whole framework here that I find very pretty. But I don't have time to go into any of this. So, but this is just a tiny flavor of that. So that was in my paper, Skew Structures in 2016. All right, so those are 3 examples. And I will tell you maybe a little bit more, another example. But first, I want to tell you a few curious features of skew monoidal structures, which I like as well. So the first of these is that tensoring with the unit on one side is a comonad, and it has the obvious co-unit, which is the left unit map. But on the other side is a monad. With the right unit map is the unit map, and in fact, the comonad distributes over the monad. So there's something interesting going on here that this first example hints at. There's some sort of mixture of lax and op-lax structures. And so this also suggests, so if you have a comonad, you can look at its Kleisli category, and that gives you another notion of map in your category, right? So, and we can think of these as some sort of weak map. So every skew monoidal structure has a notion of weak map from the comonad. It also has a sort of notion of right weak map coming from the monad, a morphism in the Kleisli category for that. So these are my preferred ones because if you think of maps like this, they correspond to maps from I to the internal Hom in the closed case. So these correspond to the elements of the internal Hom, which are the weak maps I sort of talked about before. Okay. So I just mentioned in the 2-categorical world, these comonads are actually pseudomorphism classifiers. So for example, in the example I talked about, you have a skew monoidal structure on symmetric monoidal categories in strict maps, but now the maps in the Kleisli category will be the ones of interest that you actually started with, so the strong symmetric monoidal functors. And so you can recover, in a sense, the weak world from the strict world, equipped with your skew structure. But mostly I want you to think about the fact you have comonads here, monads here, distributive laws, all coming from this structure. Now, another very important property is that we have duality for these things. So if you have a skew monoidal category, the opposite category is also skew monoidal, but with a reverse tensor product. Okay, and if so that's sort of not totally, well, it's obvious if you write it down, but what it suggests is that skew monoidal categories are neither lax nor op-lax structures, because if you take a lax structure, the opposite category is generally op-lax. So for example, if you look at things like lax monoidal categories, if C is lax monoidal, its opposite category is op-lax monoidal. But here we have C skew monoidal, implies its opposite category is skew monoidal too. So there's some weird sort of mixture of lax structures and op-lax structures that I don't really understand. So it's some sort of bilax structure. Again, the distributive law hints at something like that. Okay. I will mention that this also isn't particularly obvious, but skew monoidal categories do actually have an associated lax monoidal structure if you know what they are. This isn't totally obvious because you would expect that if you want to take the tensor product of n things, you would just multiply them all in it with the bracketing on one side or the other, okay? But that doesn't work quite. And what you have to do is you have to stick a unit on one side, okay? And that's the fundamental reason is because this object classifies sort of weak multimaps because you've stuck a unit there. So it's sort of connected to the Kleisli thing. But so it's an interesting fact that these Skew structures do have lax monoidal structures. And since they satisfy duality, they also have oplax monoidal structures where you have a right bracketing. Another thing I find it very interesting, but I haven't been able to fully figure out what it means is there's many analogies between this concept and that of an algebraic weak factorization system. If you've ever heard of those, it's another sort of, it's a sort of generalization of a orthogonal factorization system where you have monads and comonads around, and they give rise to both lax and oplax factorization algebras. And there's, but I'm curious about understanding these, in what sense these sort of structures are bilax a bit better. So let me sort of finish more or less by telling you a bit about the part of the picture that I didn't tell you about, but mentioned in the title. So, and that's about the multi-categories. So monoidal categories correspond to these representable multi-categories of Hermita. Lambeck had, I think, described the correspondence between biclose multi-categories and monoidal closed categories and stuff like this, or representable by. Lambeck had hinted at some of this in his original papers, but Hermita has the correspondence at the level of monoidal categories. There's a later result of Manziuk, who shows that closed categories correspond to certain multi-categories as well. Now, so what is a Skew multi-category? What's the Skew version of this story? Well, I can introduce it in this way. So the thing is, so we've been thinking about Skew stuff, and we've started to see that there's different kinds of maps around. You sort of have strict and weak ones, okay? In the Skew world, you have at least two kinds of maps. So in a Skew monoidal, or in a Skew multi-category, you're going to have an ordinary multi-category of loose maps. So we just use the word loose. And so for n greater than 0, you also have a collection of tight multi-maps, okay? So, and the idea is you can view tight ones as loose ones, okay? And so you have two kinds of multi-maps, and then there's some extra substitutions and conditions, but so there's a very nice, so this is a special case of a T multi-category for T a certain, say, operaton cat or two monad. So that's a theory people kind of know. And at this level of generality, that's a better way to introduce it. I don't want to tell you about that, but what I do want to say is, I don't want to give you, say, some elementary definition of all the equations, which would be horrible. But what I can say is that in the special case where these maps here are just inclusions, so the tight maps are special loose maps, right? You've got a multi-category and some special multi-maps. The extra conditions that you just need are very simple. So the identities are tight, and the other condition is that if you have a tight multi-map, and if you have a series of multi-cat maps and you compose them by substitution, if F and G1 are tight, then the composite is. So this is something about sort of the first variable. And okay, this is very fast, and I just want to say what the idea is. So you should think of these tight multimaps as sort of strict in the first variable. So you can think of a tight multimap as a multimap which has some special property in the first variable. And basically what the conditions require is that these sort of multimaps with special properties in the first variable are closed in a way under composite substitution. And so basically all the two categorical examples come from these sort of things. And we so I'll just finish. I'm not going to get through this properly, but so Steve Lack and I had a theorem describing a correspondence between certain skew multi-categories and skew monoidal categories, and also with skew closed ones. So I've got some ongoing work connected with this with Gabriel Labia. And I'll also mention that Ustalou and Zeilberger and various co-authors have been studying the connections between these sorts between skew monoidal categories and variations of sequent calculi, which are very closely related again to these skew multi-categories, in a way inspired by Lambeck. And they've been using these sort of approaches to give coherence, approaches to coherence theorems for skew structures, which is quite interesting as well. That's something I want to understand better. So that's another connection, say, in the skew world that builds on the original insights of Lambeck. I want to understand that stuff a bit better. So this has been an introduction to skew structures, and I hope you got something from it. So thanks for listening.
Great, thanks, Sean. So everyone can unmute. Some people are putting the clap emojis, but thanks for the talk. We still don't have our clapping system down yet, but yeah, that was great. So, so people can unmute and ask questions, or raise your hand in the reactions button, and we'll. Looks like we have a question. Nathaniel, do you want to unmute?
Yeah, thanks for that talk. That was a really nice overview. There was one vertex of one extra vertex of the triangle at the start I sort of expected to see, and I was wondering if you could say a few words. So another structure that's related to all of these are promonoidal categories, or skew promonoidal categories. I was wondering if you could say a few words about how those relate to the multi-categories, the closed categories, and monoidal categories.
Right. So that's true. So you can define say skew monoidal or skew pseudomonoid in a say a monoidal bicategory type context. And if you look at it in the bicategory of profunctors, then you can identify skew monoidal categories as these skew monoidals with certain representability properties. You can also identify skew closed categories as certain skew monoidals with a sort of representability property on the other side. And so that sort of approaches how in one of the papers with Steve Lack, we showed this correspondence between skew monoidal categories and certain multi-categories, and then we deduced the corresponding version for closed categories using it, using the viewpoint of both of these structures as certain skew monoidals. But in prof, I don't think I have an exact sort of correspondence type statement worked out in my head that I can say to you to build on that. But that's all I can say for sure.
Thank you.
I think before we get to Valeria, someone in the chat asked, Constantine asked, does the skew HOM include examples such as the measuring coalgebra between algebras?
I don't know. I haven't thought about that. It sounds like a good question, and I have to say that something I'm very interested in is hearing about more examples and applications of these skew structures to, say, non-standard types of situations. So I think it would be very interesting if that was the case, and would like to would encourage you to investigate it.
Great. And Valeria, do you want to ask a question?
Hi, John. Yes, do you mind going back to a slide on the Eilenberg-Kelly theorem?
Yeah.
And very much at the beginning, yeah.
No problem.
Because it's a question about your motivation and philosophy somehow, right? Because you see, the point, go down a little bit, because you kind of, I wanted to see the bit where you say how many things are invertible in each side. Yeah, kind of that's cool. Because you're paying an awful lot of attention to this idea that there are 3 invertible maps in the monoidal case and only 2 invertible maps plus this T in the in the case of the closed things. But if you go back to logic, where I am coming from, and then your intuitions are very different, right? You think of things very different from the way I think about them. And there, the closed structure ought to be much harder, because monoidal structures kind of live really within the same universe, whereas closed structures kind of correspond to implication, and implication lives in a higher kind of universe, the universe of things that kind of have to talk to the outside. So, I wonder why the fact that you actually can make this imbalance into a balance is actually very surprising to me. It's actually, I wouldn't have expected it. And then, the whole idea of the skew structure looks not very logical in the sense of Curry Howard, if you see what I mean. That was the question, sorry. It's kind of, as I said, it's more about the philosophy of it.
No, that's very interesting, and I don't know if I have anything to sort of reply to it. I can only say that I can imagine that you have a very different, that you look at these sort of correspondences with different things in mind coming from logic, or maybe connections with lambda calculus or something. And I suppose this is just my particular story of how thinking about other kinds of examples. It seemed quite a natural line of thought, but So it seemed like a good line of thought from some sort of direction, and it leads to interesting stuff. But it might not be.
I think it's very interesting think about it, it probably is connected to the stuff that you were talking at the end about the ways of thinking of multi-categories and connecting them, right?
Yeah, yeah. So there's this work of, I suppose this is connected to the sequent calculus of Skew multi-categories in the sense of Oosterloo and Zeilberger and collaborators. And the idea there is that, you know, they have the so-called stope or whatever they call it. So you have various sequences on the left, but then you have a sort of extra object on the left, potentially on the left of those sequence. So you can have two kinds of sequence, one corresponding to the weak multimaps, and so they have a kind of they have some different variations on the classical sequent calculus corresponding to this world, and I don't have a great understanding of it yet, but so there's a whole bunch of papers being written about that kind of stuff, and I hope to understand them better in the future.
Yeah, no, that's very, very interesting. I mean, I really love to see the description that you've made. Kind of, I mean, was very good for me because it is very algebraic and kind of, you know, as someone was saying in the chat, very much about category that's even before my time, you know, in the 60s and stuff. So kind of very, very nice talk. Thank you so much. And I will try to read the papers that you mentioned.
I should say that my reason for giving this talk is because I want to sort of try and sell these Skew structures, and I think they're quite interesting, and just bring them to the attention of some more people who maybe hadn't come across them yet. So I'm glad that you found it interesting.
Now, I found it very interesting. And one more thing on that, you know, if this extra place is some sort of stoop in kind of in more logical terms, you know, it's undermining again your idea that these two things are the same, right? Because, you know, this position, the first position there, the one that gets the eye, it's very special. It's different from all the others. So, you know, a multi-category, at least in my head, it's very symmetric. And in this case, it's not, right? You know, the
That's
first
right.
step, first position is really special.
Yeah, definitely.
Thank you.
Okay, thanks, Valeria. And Andreas, maybe we'll have one more question and then break.
Yes, I have. I'm not sure it's a question. It's a meta question. What should my question be? So part of what you were saying reminded me of something that has the unusual name of basic logic. It was developed by Wim Rautenborg probably 30 years ago or so. I don't remember exactly, and I don't remember very much about it either, but I do remember there were things like there's a distinction between a sequent being provable from A to B and the implication A implies B being valid. This looks a lot like, well, this reminds me of the distinction that you were making between the genuine morphisms of the category and these other things that appear in the internal Ham. And I'm just wondering whether, you mentioned in one slide that I think Oosterloo and Zeilberger were working on connections of this with logic.
Yeah.
I wonder whether this basic logic is one of the things that appears there, or is this just something?
I haven't. So I honestly couldn't tell you. My suspicion is that I have looked at those papers. I mean, browsed through them a bit, and I haven't seen anything about that. But perhaps it sounds like a very interesting question, and I talked to Noam Zeilberger, so maybe I might mention your comment to him. I might send him an email or.
Okay. Unfortunately, you know, Googling basic logic will produce all kinds of stuff other than
that's
this system. So it's
what was the author? What was the author again?
Is Wim Rautenborg. it's a Dutch name, so it's spelled Ruitenburg. Maybe I should just put that in the chat.
That would be great, actually.
Put this here. I hope I spell it correctly now. Last time I tried to put something in chat, I had a typo, but I looks like I got it. Ruitenburg.
Okay. Perfect. I've made a note of that anyway, and I'll try and pass that idea on if that's okay.
Okay, sure. Thank you.
Great. So I think what we'll do is end the live stream now, and then, but before we do that, let's thank John again. So thanks again. And okay, so we'll end the live stream, and anyone who wants to stay on, if you have more time, John, maybe there'll be a few more questions. It looks like